Hello, I would like to give now the fifth lecture on Calculus 1. Let's call it correspondingly. Calculus 1. Actually, also, as I told you, maybe the more suitable name is Analysis 1. Fifth lecture. I'll first briefly recap what we did last time. Last time we just considered the intuitive limits, arithmetics for sequences, and the considerations of these limits arithmetics, especially corresponding proofs of the simple arithmetics operations on limits. They yielded a huge wealth of intermediary results of lemmas that we needed to actually prove the simple arithmetics. Yeah, and we finished just proving that if it exists, then the limit of the division of the sequences where division is then always meant member-wise is of course just the division of limits of those sequences. All right. What is the plan for today? I'm not sure yet how exactly we will proceed, but certainly what we have to consider currently is a limit of a special sequence, and we will use it a lot, of the sequence. Well, actually, I'm not so sure. Yeah, okay. Okay, of the sequence x, and I have not introduced x. Quite unusual for mathematical objects that I have not introduced it, but I'm talking about it, but just say that x is a fixed real number. And we should most suitably call it sequences because we are particularly interested in the limits, and the limits will be different. You can already see it by thinking about x being 2 and x being 0. In one case, we get that this sequence blows up to infinity, of course, when we take 2. And in other case, we get that 0 to the power of n is always 0. And this is like a building block for a special type of function. You probably recognize that for the functions called polynomials. That is one of the reasons why this sequence plays a special role, which will come up in different contexts by our considerations. But it is also a sequence that pops up in different contexts just by itself, even without thinking of explicitly polynomials. Okay, so sequences here is related to the choice of x. For different choices of x, we would get different types of sequences. Okay, then another thing is, and this is a big stuff, but well, after finishing these two, we'll be almost done. There is a third topic remaining. I'll talk about it in a second. Cauchy sequences. Completeness, that is property of structure of R with respect to the sequences, namely that Cauchy sequences. Cauchy is a special property that we will yet have to define, that Cauchy sequences always converge. And it will turn out, and that will be rather easy after we have defined the Cauchy property, that every convergence sequence is actually a Cauchy sequence, so that convergence or being Cauchy is an equivalent notion in R. And just a little bit looking behind the curtain into the more general mathematical world, we should note that this property of convergence being equivalent to Cauchy property is not at all a trivial thing. Not all sequences that are Cauchy sequences will be always convergent. This property is a nice property that we actually always want for mathematical objects where some numbers play a role that we consider. And being a convergent sequence implies being a Cauchy sequence in metric spaces. A metric space is a special notion of space. For example, R is, of course, a metric space, but we didn't talk about metrics yet, but it is just some generalization. Metric spaces are kind of spaces with numbers, but not with numbers. It's just that for now we only know numbers. That's why I'm using the most familiar notion to you. So it's kind of spaces of some objects that in some sense might be considered like numbers. So their behavior might be considered like behavior of numbers in some sense. Not exactly, and actually that's rather wrong, but yeah, just for you to have some intuition. And for those metric spaces, completeness is a nice property. Generally, completeness is a nice property. Yeah, and in even more general spaces that are no metric spaces, and yeah, pay attention, I have not defined metric space. That we'll do in analysis 2, I guess. Um, in even more general spaces, even Cauchy property, if I recall it right, there I might be mistaken, even Cauchy property does not necessarily follow from convergence property. But convergence in more general spaces is not that trivially defined as the convergence that we defined for sequences. I don't mean that the definition is trivial, but compared to the more general stuff, it is rather trivial. So just so you have an outlook also for complexity of the stuff that is generally present in mathematics. You should not be overwhelmed by this imagination, but you should just have this imagination that mathematics is much broader. And I would recommend personally that you perceive it with awe, with awe and high expectation for what mathematics can give you. Intellectual sense, in sense of modeling the world, in sense of mathematics itself, of what mathematical world uh, has to offer you of surprises and things like that. Okay, and the last thing we'll probably look at, I'm not sure yet, but I guess sequences approximating roots. Because for now, we actually cannot use the notion of the root. Probably you remember in one proof, I think concerning absolute value, I told you that you have to prove it by way of case distinctions, even though there was much simpler proof uh, using roots. But we can't use even square roots because we don't know if square roots exist. Of course, for things like 9 or 16, we could think of square roots. No problem, we would just define for natural numbers that the square root exists when there is a natural number that multiplied with itself gives us a number. No problem with that, right? And multiplication of natural numbers, I think we defined briefly. There is nothing new. It is just using the distributive law on those one representations, right, of natural numbers. Okay. And this multiplication, of course, acts like our familiar multiplication. Okay, here you can define a square root very easily. But for such things, that such a number, of course, plus when define square roots of negative numbers doing complex numbers, do that. But yeah, we are now talking about real numbers. And for these things, and also zero is included, of course, in general, to define something like square root of 2 when a natural root does not exist, this will be quite non-trivial, meaning that if you just look, is there a number y in R such that y is actually a number whose square is 2, then that's a big question. How do you show that such a number even exists for every positive non-negative real number in general? How do you show that? And you have to show that because you have defined your real numbers as what? As we have defined them. And as we have defined them, we have to have everything what they should offer in our opinion. Because this is their fixed definition and this everything else is determined by this definition or should be determined by this definition. And indeed, this definition implies the existence of square roots and more general n roots, but we have to show that. Okay. Sequences approximating roots. And I'm not sure about this one because I plan something very special. I don't remember how the sequences are defined, and I would like to just try to think ourselves how the sequences can be defined, just to come up with the definition, because I don't remember this definition. I wouldn't know. So I would have to do it because I don't want to look the definition up. But yeah, it would be something rather special and maybe very lengthy. So I don't know if I will do that. Actually, it's quite exciting. I'm looking forward to this lecture, but I do not know yet if I will really do that. Here is if we will need roots, of course, we will have to prove their existence, but then I'll just do a supremum proof. I won't do the sequence thing, but I would love to do the sequence thing because there we will really be on the path of mathematical discovery, even though it will be discovery of some new America, so some new something that has been already discovered. Okay, we will invent the whatever it is called in English. We will invent the wheel again. Yeah, but yeah, we'll do it by ourselves without knowing how it is actually done, and we will just use logical reasoning. So it can be quite exciting because it will be explorative journey. Really, I don't know at all how it's done. I remember the general technique how to prove that a sequence that is defined somehow, or this sequence maybe, I don't know, converges to roots. I kind of remember very blurrily scheme, but yeah, we'll see if we'll do that. I'll probably try to do that, but if I upload that, I don't know if I will even succeed in doing that. Yeah. Okay, well, I wasn't sure about the order, but let's try maybe to show, yeah, let's try to show first what are the limits of a sequence. And yeah, let's start with this. I think I already used that terminology, but I also explained it underway, so it's no problem. Definition. So we had those convergent sequences, right? Those were sequences that for every distance from a designated number, special number that is kind of associated with the sequence, for every distance we achieve this distance, that is, we think of distances getting ever smaller, and they stay from a certain point onward at this distance that we have achieved at the very least. That is, they could even get closer, but they don't get longer distance anymore to this number. right? And now we define divergent sequences. And in general, divergent sequences are just sequences that do not converge. One, uh, divergent sequence, that is emphasis, that is not put through a word line. A divergent sequence an n 10 is a sequence for which no limit exists. If we wanted to phrase it in a very difficult and overloaded manner, we would say no real number has the property that it is the limit of the sequence. That is, for real numbers, for the real number, that is like for R, it is not true that R is the limit. And then we could also negate the definition of the limit, but well, it suffices actually to understand that on this level, but you should also think that it would be possible to phrase it in that overall loaded way. I don't remember any instance when it is really explicitly used, this formulation. Maybe it is used, but nonetheless, I don't think it is ever used explicitly in that way. Maybe in some ways that touch this implicit definition. So divergent sequence is just a sequence that does not converge. So there is no such behavior with respect to any number. But yeah, technically it is for any number, it's true, this number is not a limit. Okay. And infinity divergent sequence. And we denote this property like limit of the sequence is infinity, but you should understand that it is not saying that the limit is equal infinity, it is just written like that. And we could also say plus minus infinity divergent sequence. That just means also denoted n to infinity plus minus infinity. Alright, an example would be -1, -2, -3, -4, ta 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 ta. That sequence diverges to minus infinity. 1, 2, 3, 4, ta 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 ta. This diverges to plus infinity. Right. But pay attention again, it doesn't mean inequality in the sense that one mathematical object is equal to the other mathematical object. At least in our model, not. This equality is not really meant as equality of two mathematical objects. It is kind of like abuse of notation. We don't really mean equality. We mean that this notation expresses the tendency of the sequence, and it is the following tendency. Is a sequence a n and n such that for all n element n, no matter how large, there is some let's call it uh, m and n such that would be let's uh, such that, but actually to mix quantifiers and to mix words is not a good habit. Of course I'm doing that, but yeah, actually you should choose either use quantifiers in an expression or you use words. To mix them is not a good manner of mathematical writing, but yeah, people do that. And also an important note, don't think that mathematical texts, maybe it will be relief, maybe it will be a frustration, but don't think that mathematical texts are entirely written in quantifiers. It it is not done like that. You will see more words than quantifiers actually. So people use natural language, but in precise mathematical way. Usually quantifiers in mathematical articles, well, you rarely meet them actually. But yeah, the idea of quantifiers is you get used to this meaning conveyed by those mathematical words, in that you see them first as a student as a single symbol. So you get used to those firm mathematical framework of words expressing the exact thing that it has to express. That's why we are using quantifiers for now. And of course, I'm also lazy, clearly. Okay, well, for all n bigger or equal m, we just have that a n is bigger or equal, or respectively small or equal, and that is plus or minus infinity. Oh, sorry. Yeah, that's nice. No, of course not. Plus minus n. You see, if you just forget the minus for now, and you'll just see that your sequence for each n will reach this n and will stay above this n, so that eventually the sequence gets as high as whatever, and it stays there indeed. So similar to the definition of convergence, right? And here same, but it just goes down infinitely far away. And how do we express that? Well, by using all. For all natural numbers, we get below the respective number, and we stay there. So it's a tendency of getting there and staying there. So similar like in convergence, right? Okay. Okay. Well, I think we'll be able to consider this limit right away, but yeah, not sure yet. We will see. Okay, let's call it theorem. And what would we like to prove? Well, no, that we actually cannot do. Okay, theorem for the sequence so we choose this number x and r, and well, we consider the sequence a n in n is sequence x to the power of n and n. Okay, have, depending on the choice of x, have a limit x n to infinity. And we mean by this now, of course, limit of the sequence, as you can guess. This is just the sequence, so we could write here sequence as well, right? And we have infinity if x is bigger than 1. We have 1 if x is equal to 1. We have 0 if x is equal to 0. And these two cases I won't prove, of course, because kind of trivial, right? And we have well, actually, okay, that will become really lengthy. Let's put that also here, right? Then we have for modulus of x is smaller than 1, absolute value of x is smaller than 1, also called modulus. Then we have we already know. Then we have 0, that is if modulus x is smaller than 1. Then we have, well, and of course, for x is smaller than 0, it is divergent. It is divergent in sense of not having a limit, and it is not even divergent to infinity or minus infinity because it alterates, right? Divergent for x being smaller than 0. And that is why I chose this kind of inequality, because equality divergent, of course, doesn't work. We haven't introduced addition with equality for divergent. That is why I choose that. But it is clear here we apply equality, here we apply this. But also pay attention that this equality is of special kind. All right. All right. All right. And that for negative numbers, it is divergent is clear, right? It is because, well, if we have a negative number, right, and we just know that this number is actually an inverse, additive inverse of this number, right, and minus a is now a positive number. I mean, our here that is just so with properties you can think about it why that is. But yeah, it's just definition of inverse. And now we know also this can be written like this. And if you are uncomfortable with this minus minus, I can redefine that as simply tilde, and then I have tilde, which gives me then minus 1 a tilde to the power of n is equal to, well, minus 1 and minus 1 n a tilde, and which will alternate between, well, let's put it like that, if we have a tilde n for n even, that is n divisible by 2, and we have a tilde n minus a tilde n for n odd, and that is the sequence will jump, right? It will jump positive, negative, positive, negative, positive, negative, and it will really jump, meaning that for 0 we are for 0 we are at 1, from 1 we jump to no minus, right? So if we have such a negative thing, of course, have to put that absolute value is bigger than 1. Otherwise, we know what happens when it is equal to 1. Actually, a bigger or equal 1. Because, yeah, for -1 it already works, but for absolute value being smaller than 1, indeed, we nonetheless get 0. Right, but for this, it just alternates, right? So for n equal 1, we are on minus a tilde. For n equal 2, we are on a tilde to the power of 2. And so it alternates for n equal 3, for n equal 4, for n equal 5, for n equal 6. Of course, it is not necessarily symmetric, but I wanted to show the tendency. Of course, here we have somehow squared. Here we have just this 1 multiplied by that, so this is higher and so on, but I wanted just to show the tendency that we jump there, there. So this never converges to infinity, no converges, of course. And that is what we have then. And this part I won't prove because it's kind of trivial. You can prove that if you want. Let's say that that is proof homework. If you wish, because it's too clear. Mathematics is certainly about some things that are not clear, or things that are not clear how to construct them properly. So if it is not clear to you, then yeah, of course do that. Okay, and what we will show that is, so I won't even write proof homework because I hope, sincerely hope, that that is clear, right? Here we use the property that 0 multiplied any number is 0, and you will just use the additive, the multiplicative neutrality of 1. Right? Okay. So these two cases remain. Case x bigger than 1, and case modulus of x is smaller than 1. Oh, okay. Proof of cases. Modulus of k smaller than 1, and x is bigger than 1. Okay. So first, we consider the case is bigger than 1. I think it is easier. X bigger than 1. Okay. Well, let's think about it. How could we prove that? I think we have shown, well, we have had that supremo thing, and we have shown that there is no largest natural number, right? Within the theorem, we have shown there is no largest natural number. Okay, well, could we use that here? Oh, there is no largest natural number. Means that there is a natural number that is bigger than x, right? All right. Well, bigger than x is not what we want. Okay. So, well, yeah, let's talk about define. And this just notation, right? We define such a function that, and we do not necessarily write it as a function, because it's just so customary to just write this, like apply this operation to to x for x element r, we can just say okay. Okay, we do this x element r. My general definition is better. So of course, do not confuse you in our time. I should just take in better, but okay, I'll do it like that. And this is defined as the maximum. Of course, not as a set, but as a maximum of the set. And maximum of the set just the maximum element of the set of natural numbers. Of course, of the integers, not of just natural numbers. Okay, I don't need to write it like that. I should just write it as integers, and I understand that I'm kind of going too fast. Should concentrate better. Okay. Don't be confused that I write n here. The symbol doesn't matter. The meaning is given, right? And C with the property that x. Right, so the biggest number that is below x. Right, and well, how do we know that such a maximum even exists? Well, you see, since natural numbers get as large as whatever, there is a natural number that is bigger than x, right? Because they get bigger than any real number, as we already know. We have shown that in one of the theorems, right? Maybe not as an additional theorem, but we have shown it by the supremum property that there cannot be a number that bounds natural numbers, and that as the contrapositive means that the natural numbers get larger than any number. Okay. Oh, so there's a natural number larger than x. Then if there is a natural number larger than x, then all the natural numbers that are smaller or equal x for m small equal x, we get that this m is smaller or equal this nx, right? All right. But now, then those numbers are, of course, in the interval. That implies, this is just untidy notes, right? That implies that all those m are in the interval. We didn't introduce interval notation. We should do it actually. We should introduce the interval notation. I'll do it in a second. But for now, we didn't do it yet. Well, probably not in a second, but yeah. Okay, that is between 0 and nx. Right. And this set certainly has only finitely many elements because, as we know, this set consists of the sets of course I mean intersected natural numbers, because I'm only interested in natural numbers here, and I'm trying to show that this maximum it exists, right? This consists just of those sets. X minus 1 and x. So that is this set, which is equal to this set, this union, right? Union union consists of finitely many elements. Right. I have already written here that instead of between n x minus 1 and n x, and also I should not use x here because that could be confused with that x here. Should use y here. Okay, and here I should write it properly first. This set is of course finite in total because that intersection in total, that intersection is just equal 0, 1, and that intersection is just equal nx minus 1 and x minus 1 x, right? X minus 1 and x. And in total, we just have all those elements, and this is certainly a finite number of elements. Well, and there is a simple lemma that you can prove if you wish. We just take it for granted, but well, it is not difficult to prove. For any finite set, any finite set M subset of R supremum M maximum of M. Ah, yeah. Sorry, not like that. Supremum M is element of M. We know supremum M exists by supreme maximum, but now the supreme itself is element of M. Then define maximum of M supremum M. And finite set, you recall, there is a bijection onto a set of 0 ta 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 n of natural numbers onto this set, right? But yeah, you can just think of finiteness in terms of how we perceive finiteness. You could also translate, you could derive all the things that are specific for finiteness from our definition for finiteness. No problem with that. Right, and let me maybe tell you briefly how you prove that. You can then fill the gaps. Well, yeah, it's easier. You have just to use this property of with epsilons. You just assume, well, um, the supremum is not in the set or something. If the supremum is not in the set, then you just have infinitely many. Then you will just have an element that is certainly okay. Well, let me think. Yeah. It's simple. If you recall this property, right? This property that if S is supreme of M, supreme of M, and for all epsilon bigger than 0 is even equivalent if we additionally assume that S is an upper bound, right? For all epsilon bigger than 0, we have that exists X and M such that S minus epsilon, so as soon as we reduce by epsilon, that is already smaller than X. Right, and if we have a finite set, and we just assume that this holds, right? Then we just take, well, take okay, we have to again to have the maximum to be able to do that. Well, yeah. Haha. Okay, well, now, uh, how do we show the supreme of M is in M? Do it differently. Do it directly by this, but not but informally. Just do the induction. Induction on number of elements in the set. Number of elements in the set. Yeah, that's simple. We don't need to do that. Probably it would also work, but it's simpler just to do induction. And clearly, we have one element, then maximum is this element itself. I mean, the supremum is this element itself. If we have two elements, well, then for each of them, the supremum is the respective element, right? Yeah, but we have done it for one, so let's assume we have done it for n, and now we have n plus one, and we can just take n, and we take their maximum, and just another element is joined with n plus one with n to this n elements, so we just take the maximum of those both. And just by definition of the maximum of two elements, or maybe we have before that to define maximum of two elements, but I suppose it's self-suggestive how we define maximum of two elements. Yeah. Okay. We have to do it also for two elements to just apply that properly, but for two elements it is not difficult because we just have that the maximum. We have also proved uniqueness of supremum, you remember. So, and the supremum, the least upper bound will be just the maximum of two elements, right? Will be just the larger element. And that it is larger is kind of obvious. Yeah, okay. It's simpler. It's simpler. We don't even need that. We just need to look at those. And that set, we find many elements, and we will have that the maximum of this set. This the no. We won't have that because we haven't shown yet that this maximum even kind of exists. We don't know if maxima in that regard exist. We can choose them out of the set. So yes, first for two elements, we have to show that the maximum of two elements is the supremum. But since it is upper bound, and you can show easily that it is the least upper bound, there can't be a better upper bound. It is even very easy because a smaller upper bound than one of the elements would already place one of the elements would already be smaller than one of the elements in the set, and so it wouldn't be an upper bound simply. And then you apply that maximum of two elements by induction of number of elements in this set. So, and that I have shown that you so briefly. You can fill the gaps if you wish. That already indicates that we kind of switched the level, and indeed we switched the level. Those easy proofs I will rarely give from now on because those are just, well, you should be able to do them yourself now because, well, you have already seen enough mathematics to be able to do that, right? So that filling little gaps you have to do it yourself. Okay, and you should really do that. You should really do that. Better not accept anything, just like I did not accept anything back then, but fill the gaps really. Okay, but it was not formal discussion, right? I told you how to do that, but yeah, formal, it was not formal. It was just some quick notes how to do that. Okay, we take that and we have that maximum. Okay, well, that is the maximum and that is smaller or equal x, and you can prove yourself in x element of the set. Remember, that is a number, right? That is that down bracket of x is of course a number, a natural number, namely. So that is that. No, in general an integer, but in our case, natural number where we have that bigger than 1, right? Okay, then have, of course, you can prove that if you wish, x minus a down bracket of x is smaller or equal, actually would be never equal, right? Because that would be already then the down bracket will be already that thing, so x would have been to be that thing, right? Because we take the maximum number that is smaller or equal, and if we suppose that x is equal to this, well, then this number would not appear, and we would just be already here. So x will certainly be below the number that comes after down bracket. Right. So x will be below this number that comes after down bracket, because that is now in relation to x, right? This number is related to x, and it is in maximum, that is this is more equal, right? And then there are only two possibilities: it is either small to this down bracket, or it is equal to this down bracket, or it is this down bracket is either smaller than x or it is equal to x, right? Right, so this equality is impossible because the largest that this down bracket can be is no the smallest that this down bracket can be is actually no the largest that x can be is the down bracket, because x is supposed no, sorry, okay, got confused, kind of a little bit unconcentrated now. The down bracket is okay, we talk about the down bracket, and the down bracket is certainly the largest than x can be, because the down bracket is supposed to be a natural number that is smaller or equal to x. Okay, the down bracket is the down bracket can be at the largest equal to x. Okay, the down bracket can be at the largest equal to x. Then, but x itself can be or must be always smaller than the down bracket of x plus 1, because that is the maximum of all n's that are smaller or equal x, right? So if that is the maximum, then this maximum plus 1 this maximum plus 1 should already exceed x, because if it did not exceed x, if our maximum did not exceed x, if our maximum plus 1 did not exceed x, then that would mean that our maximum plus 1 is smaller or equal x, and then the down bracket would be smaller or equal x minus 1. But if it is smaller or equal x minus 1, then the down bracket would be certainly, okay, I have to write it down. So the down bracket would be x minus 1. Yeah, okay, I have to think myself a little bit why it is well defined. But yeah, I'm noticing that I'm slow now. Okay, so we're defining it like that. And we want to exclude case that x is equal to this, right? If x is equal to this, then x minus 1 is equal to the down bracket, right? And then x is of course bigger. X, I mean now x minus 1 is equal to the down bracket, and that is x minus 1 that implies that the down bracket plus 1 is equal x. Okay, from here we don't have that actually. The down bracket might be, yeah, but then yeah, that's your point. Okay, got it. That is a natural number, right? And in this down bracket wasn't actually a maximum. Yeah, this notation confused me a little bit. Because yeah, to formalize why it is true, kind of because there are explicit formalisms, like we have defined it like that, and then there is a contradiction involved. But since there are such formalisms involved, it's not that that's that obvious for immediate thinking. Yeah. Okay. So we have assumed that the down bracket is actually maximum of such n's that are small or equal x, right? Okay. But then now that is x is equal to this, right? And then this is actually equal to the down bracket by definition, because it is a natural number, right? It is a natural number. and it is certainly small or equal x, because it is in particular equal x. And so that is equal to the down bracket, which is a contradiction because that implies 1 equal to 0. Right, okay, then we have that this, you can prove it yourself. Okay, it's too easy. It's certainly smaller than 1. But that is also bigger than 0. Actually, bigger or equal to 0. Because if, and it is equal to 0 if and only if x is nature, of course. Otherwise, it is just included between those two. And what did we do? Well, it's just something like 5 versus 7. We don't have this notation yet, but since you understand this notation, I will use it. So we have that. Right. But of course, we don't use it in the formal treatment. I only use that to illustrate. All right. Okay. Well, what does that actually mean? Well, we just let this be an epsilon. Okay. Well, then x is equal, which is a natural number, and that is epsilon. And we just define it, and this is a little bit of abuse of notation. We just define this natural number as n. So basically, when x is bigger than 1, what do we have to show? We have to show then that this sequence, and don't confuse it, maybe I should call it m. I have to show that m plus epsilon to the power of n, right? That was our sequence, and element of n. And we have just given another form to the basis, and that is equal to infinity. Right. Well, here is a good exercise for you to do induction. It's called exercise. So, by induction, that for yeah, and pay attention for this induction proof. You will need certain identity between binomial coefficients, but you can just think how you will come up with this identity and what binomial coefficients are. You'll see in a second, but first let me write the formula so that for a, b, and r, and they are really chosen arbitrarily, have, and yeah, this proof I have given in one of my videos. I don't think it was basics of university maths, it was one of the school videos, and this proof can be done rather easily, but to formalize that process you have to go by induction. For A, B, not to formalize that process, but to give a formal proof. It is not actually formalization of a process, but it is like dealing with formulas and symbols. Show by induction that for A, B, element R, we have that A plus B to the power of n is always equal to I equals 0 till n. And here you have something that we will define in a second that is called binomial coefficient. And you have, so this is mathematical notation for something that we don't know yet what it is. All right, and yeah. or maybe customary way. And here you have a product of powers of b. Right. With definition binomial coefficient, and by the way, binomial coefficient has a very nice situation. If you never saw that, then you should Google it, because the definition of it appears the first case when you don't think about what it means. Rather weird, maybe. You think that it is difficult to think of such a definition, but then just Google the intuition. I would probably make a video about it eventually, but yeah, it is a rather simple topic, so I would not like to really make a video about it. So yeah, you can Google it. Binomial coefficient is defined as, but yeah, the intuition is very nice, and yeah, you should think about it. And a rather short explanation is that you just count how many possibilities there are to choose certain objects in a certain way from a collection of objects. But you should Google it to understand what is really going on and why it is defined like that. Okay, definition binomial coefficient is defined as we need the notion of factorial. I hope you are familiar with factorial. Well, first we need another definition. We need definition of factorial. That is kind of a definition within definition. Factorial for k, and then define k factorial is equal, well, that is just 1 if k equal 0 or 1, and that is k multiplied by k minus 1 multiplied by k minus 2 multiplied by blah 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 up to 1 for k not equal 0 or 1. So only for k element n we define factorial, and then we define the binomial coefficient as just such a pair of numbers, right? Let's say L and K. And that is defined as, well, you just have k factorial, you have k factorial, and you have L factorial. All right. So in particular, do we have, well, the binomial coefficient is kind of the number of ways to choose k objects out of L objects. And why it is that? Well, you should either think about it yourself or you should Google this intuition. Right. All right. Alright, so we are using this notation, and exercise you should show by induction that this is true. I will use it. Okay, well, with the result of the exercise, by the way, the proof by induction is not that difficult. But here at a certain point, of course, in the induction step where you use action hypothesis, you will have some thinking challenge. And well, there you should just see how you do that. Okay, with the result of the exercise, have it's an important point. That epsilon is actually bigger than 1 and small, bigger or equal 0. Right, and now you have the sum. Let me check briefly. Yeah, that's all right. Now you have that sum. Of course, our A and B are now M and epsilon. Right, and now you just have to show that this actually becomes and stays for n that are bigger than n, that this becomes and stays bigger or equal any given element n. Okay, what does that mean? Well, now let, just like by proofs of convergence, right, we just have to show there we had to take arbitrary um, arbitrary epsilon. Now we have to take arbitrary m in n, and we have to show there exists n element n such that all n bigger or equal n, we have that m n. Just recall that was exactly x to the power of n is bigger or equal this m. Okay, and well, what do you think is what we would like to choose our big N? Well, we just choose big N like that. Right, choose N equal M. Then, by the way, I think it could have been seen more easily actually, but yeah, it's a nice theorem how we can calculate something like that very quickly in general. So yeah, but yeah, it could have been seen maybe more easily, more intuitively. But well, yeah, actually, proper way to see this only this way now as I think about it, because that there would be some factors, some products, and all the terms positive. Well, to properly see that, we have to do that. Choose n is equal to m, and then no, that would not work, right? Because we still would not have actually we would what's the problem? Well, yeah, I would like to have okay, no, we cannot just do that. because this n, I think, never appears without this epsilon. Okay, we cannot do that. Cannot do that immediately, at least, because this epsilon always will appear everywhere where n appears. If you look at the properties of binomial coefficients at its definition, you will see that the only cases where this here appears without this here appears without epsilon, without an epsilon factor, which is as small as it wants to be. Just the size of epsilon depends on the size of chosen x, right? But of course, epsilon is smaller than 1, but it could be as small as possible, and small is bad because small makes that smaller, right? Okay. Yeah. So only in such terms of the sum there will be n appearing where we would have also epsilon. You can just look at properties of binomial coefficients and you will establish that. Okay, just by definition of binomial coefficients. Okay, because the only cases where epsilon won't appear are the cases n and I, and in those cases also n wouldn't appear because this factorial would be just, this binomial coefficient would be just 1. Right. Okay, then we can't choose it simply like that, because it would appear. But maybe we can choose it like that nonetheless, because just, well, maybe one single epsilon doesn't do much. Well, one tiny epsilon, well, let's see if it doesn't. The thing is, we can certainly get larger than epsilon, so yeah, it might do something, but let's just choose, since we are free in choosing our n, I mean our, yes, choosing our big N, right? So let's choose it appropriately. We just choose N being, and that thing is defined analogously. And you can think why that works. That is also the minimum of natural numbers, such that minimum of natural numbers such that the natural number is larger or equal the number under the brackets, and it is defined just analogously like this here. So instead of such maximum of numbers small or equal, you just let's maybe define it. Of course, you would just turn everything around. All right. So we choose that, and of course it has very similar properties, and with that have, well, you can see yourself that have for n here equal n, well, what we have is m plus epsilon n. How you can see yourself that this sum is now equal to what? Now equal to ni m I epsilon n minus I, and that this is strictly bigger because the binomial coefficient certainly support this monotony. I mean this comparison, and also the the m's stay the same. The binomial coefficients support this comparison, and yeah. Okay. No, we do not necessarily have that for now because, well, because also in epsilon this factor is ever increasing. So I mean this weight that epsilon obtains in every term, this diminishing weight is ever increasing, right? So yeah, we can't automatically say that we have if n is more or equal n. So we cannot say that. Okay. Well, but somehow we should be able to compare that, but yeah, not like that. Okay, well. No, I mean epsilon factors becomes, I mean, the power of epsilon becomes ever stronger in its property of diminishing the terms with the growing n, that is clear. So we cannot just do it like that. Okay, so instead we have first to show that the sequence is increasing no matter what we put here. Okay, well, let's think about it. Well, that's very simple. You can show yourself that this sequence is ever increasing. This is because of different stuff. It's not this property. This is simply because of our lemma that we had that yeah, that is simple. Let me write it. So that is right. We choose n's that are bigger or equal to this n, and we wanted to see why we actually have that comparison, right? Because we want this n be chosen such that this already exceeds that, and if this will be truly bigger or equal to that, then if this exceeds that, then from there onward everything exceeds the designated number, right? Designated number m. And let's think about it. Well, it's very simple. For any r, if we have some r that is bigger than 0, and from that, yeah, well, not that, I need first that, then that, and from our lemmas that we proved about the properties of that, you can prove very easily, and I think we already had that even, and you can prove very easily that by transitivity, that is for any real number that is bigger than 1, right? By transitivity, r to n equal n for, and also you could change the comparisons, of course, if you wish, because that just adds an or possibility. So of course it works, but of course also that comparison would be sufficient. By transitivity, we have for n bigger or equal n. Okay, because I want to account for case of equality, I should take this with or. And now you just look at what that is. And we just consider that all those are of course positive. So all the sum terms are of course positive, right? So that is natural numbers, so automatically positive. Epsilon is also positive by definition of epsilon as we gave it. And that is equal, well, we just take the first term in the sum. Recall that sigma just denotes a sum. And the first term in the sum would be just, well, that would be n 0, and you can compute by a definition of a binomial coefficient that taking 0 out of n is just equal to 1. That is then equal to 0. Sorry. Yeah, that works. And that is equal to 1. And then we just have the remaining sum, right? We just have written here the first sum terms, so we have to take the remaining sum, of course. Just think of it as a sum, as a genuine sum without sigma notation, and you see it immediately. And that is bigger than 0, right? But now, sorry, that's not what I wanted. What I wanted was a different thing. Yeah, so I don't have that immediately, I think. No, I actually don't have that immediately. We need to work a little bit because I'd like to have... Yeah. Sorry. Not for nothing, I wanted to eliminate the epsilon. Yeah. See, I'm a little bit hasty because it's actually quite quite clear how to do that. But yeah, I'm a little bit hasty exactly because of that, because it's not that interesting at that point. Uh, do it like that. Because I'd like to start with more challenging parts. Here it is just thinking of some computations that, as you can see, are trivial. Okay. Here's some, if we have 0, we have epsilon n, right? So no, also not what I want. What I want is actually... Okay, I could have written that, of course, too, but we just don't need that because it is a different thing that I want. I want actually to take out of the sum the situation where I get only epsilon and I get m, right? So I get this m, right? And I get this m, and I would like to cancel epsilon where we have that, right? And if it is unequal n minus 1, then out of the sum I took exactly that, and that would be something like n minus 1. Right, just replaced here I by n minus 1 because I have taken out this and I want to know what this is. To take that out, sum, and epsilon would be 1. Okay, and now I just recall the definition. We just had n factorial, and we had 1 factorial because that is just n minus 1, right, factorial. And then we had that n minus 1 factorial, right? But now recall what that is. That is n multiplied by n minus 1 factorial. Just recall the definition of factorial, because I do not expect that you see that immediately, but you can see that just calmly looking, taking time, looking at definition of factorial, and then realizing that it works like that, right? And then you have that nm and minus 1. Clearly that only makes what we have only bigger, and now we know that this is actually, recall the definition of n that we have chosen. For that chosen big M, right, to this big M, we have found such n, right? And clearly, since that factor makes it only bigger, right, and that is, well, and that is bigger than m multiplied by epsilon, since that is bigger than m multiplied by epsilon, this again just side notes, because yeah, such comparisons you should see immediately, actually. That is bigger than, bigger or equal m epsilon, multiplied by, actually, not that, I would like to have, because I want to cancel epsilon out, right? Right. Yeah, you see, by such proofs where it is only technique, they are rather boring, and you can also perceive them as boring, but you should see what is happening here. That's the point. Okay, we are bigger or equal than m when we take that multiplied by epsilon. Okay, here of course I have also to replace. So it is boring because it is too clear what is happening, and it is too clear what we have to do. Only the technical details have to be worked out. So there's nothing exciting happening, right? So, so that if we multiply it by epsilon, discounting that factor, that is not thinking of that factor, then that is of course would be bigger or equal m. But now we multiply that m by some factor that is certainly bigger than 1. And then if we apply the properties of bigger, we get that this is, of course, bigger or equal m as wished. Because that is bigger or equal m already when we look at that. And we multiply it by that, right? And that is bigger than 1. And then just by this lemma, where we had something bigger than something and another something bigger than something, then the pairwise multiplications had also same relation of bigger. So that is bigger or equal m. But if you didn't catch that, then just look at that stepwise and realize that it works like that. Usually such comparisons are uh, not even really a topic at which one stops. It is just done like an obvious thing, and that is bigger than 0, and so the whole thing is bigger or equal m. And since we had I mean here we have that equality, and here we have that equality, right? And since we have that comparison, now for all n bigger or equal big N, we are bigger or equal m. Right. And with that, this part is proven. Okay. Oh, yeah, because of that here works. All right. I know it was maybe a little bit fast, a lot of definitions and things like that. Just look at it slower and you realize that it all works. But I know it's a lot, and even though it was presented in a few minutes, you might need a couple of hours to really realize what was going on. That's normal. If I would take those couple of hours to explain everything to you, then we would not get anywhere. Right. Okay. So, okay. One case is now proved. And now the other case is what? Well, the other case that remains is just that the absolute value of x is more than 1. Okay. Let's get on with it. X is smaller than 1. Okay. Well, then we have to show that it is a null sequence. Okay. Well, what will we do? Well, observe we just use what we have just done. Bigger than in 1 x and and then diverges to infinity. Now observe x, and you can prove it yourself. That is not difficult. Just use the definition of fractions, of multiplicative inverses, and of just taking to the power. I think we have not even explicitly defined taken to the power, but of course it's obvious that it is n times multiplied. Nothing else it could be. Right, and that is just meaning that this is 1 divided by n for this sequence, and it's actually not what I like to show. We have that diverges to infinity, and now observe I don't want to have that. I want to have that. That. Remember that to show null sequence, it suffices to show that. And that this is same, you can prove if you like by induction that it follows that. Yeah. Like you can prove it by induction, but yeah, you can immediately see the induction step if you think about it a little. So yeah, no need actually. Okay, and that is equal to 1 divided by x. And hope you can see it. Oh, obviously you can see it by compare it to our definitions and think about what it means in terms of our definitions. And you have, of course, that, as I said, just prove it by Introduction, properties of multiplicative inverses. Okay, and that sequence we claimed, well, we already saw diverges to infinity. So, of course, the following lemma suggests itself. Lemma oh, that lemmas, and of course that means that we are talking about a sequence in our context. About what else? Where else could we have this lemmas notation? Plus minus in and we have what? Yeah, divergence to minus infinity. Yeah, we have defined it. So yeah, divergence to minus infinity, we know how it is defined. But then I'll just have that and let's just put it like that, because that automatically then implies that 1 divided by an is a null sequence, because the absolute value sequence of that is a null sequence. Okay, and 1 divided by an absolute value and element n is a null sequence. And of course, it might start only with a shift, maybe first finitely many values are zeros, then we cannot even define that, but then it is supposed to start with a shift. Or you could say we allow the value infinity if you like, but better to start with a shift. And this is just supposed to be, right? So we pay more attention not to particular symbols, but we pay more attention to meanings. We pay actually all attention to meanings. Right, and that is in a null sequence. Okay. But clearly, from some point onward, there won't be any jumps to 0 anymore, because, for example, from somewhere onward, we are bigger than 1 or smaller than -1, and we stay there. And from that point onward, we could just look at this sequence, because no zeros will then appear anymore. Okay, let's prove that lemma, and for this, the result follows. So we have only to prove this lemma. And our proof is then finished now from the lemma above. So, and then this for that sequence is finished. Right. Because we have exactly this situation, right? We have that this diverges to infinity. And we have that our sequence can be represented as 1 divided by the respective member of the sequence that diverges to infinity. Our sequence of interest can be represented as that. All right, let's prove this lemma. And well, this is actually very simple. Let's epsilon bigger than 0, that is any positive real number epsilon as usual. And we have to show here is an epsilon element n such that for n bigger or equal than epsilon, we have that, well, you know what that means. N is more than epsilon, because we have 0 as limit and the difference just keeps a n, right? Okay, how do we show that? Well, just we have to choose some specific n epsilon, right? But well, no. Oh, well, from divergence, and in any case, our absolute value sequence would of course diverge to just plus infinity, clearly, from divergence of actually we would like to have that. We had that sequence, and we'd like to have the reciprocal values, and we'd like to look at this sequence, right? 1 divided by n. From divergence of a n to infinity, and you can just look at that and establish that it diverges to plus infinity in any case, however, that diverges to minus infinity to plus infinity, obtain well, obtain what? Well, obtain that we multiply that by that by that, obtain for let's say 1 divided by epsilon, and let's say for larger one, right? I think it should be larger one, but maybe we'll change it in a little bit. We'll see. Obtain for what do I have in mind? Of course, I have in mind that we find such n from which onward. Well, what is that? This is just equivalent to epsilon. I multiplied by 1 divided by epsilon on both sides, right? Multiplied by 1 divided by epsilon on both sides. So epsilon is now here in the denominator, and we just multiply by a absolute value here. So if we obtain that, we have already obtained wanted, and that we want, of course, to for some an, right? So we would have that if we could have established that, but yeah, if we have now that, and of course this equivalence might not hold anymore, or probably it holds nonetheless, but I'm just showing you the idea, and that is that. And we have then from all a n onward this n, because well because we are at least as large as this we are at least as large as actually this, so it would not even it wouldn't even be this. We don't need this comparison. We just know that from there onward for this a for n bigger or equal n, we have that we are larger than this some natural number, and that is it. Okay, obtain for that there is n, and then just by divergence to plus infinity definition such that for all n bigger or equal n have that a n is indeed larger and than divided by epsilon. Okay. And should I have used in definition of divergence against infinity some bigger or equal, then of course we can replace it by bigger, because we just take this next natural number and plus 1, and that natural number, we just take the next natural number after that, so we add 1. We add 1 to this number, 1 divided by epsilon upper bracket, and well, we find some point from which all the members of the sequence, all the members here in absolute value of the sequence are larger or equal than this number plus 1, and then they are in particular all larger than this number. So it doesn't matter if it is bigger or equal or just bigger. Great. Have that. All right. Choose for this same epsilon always, of course. Choose an epsilon and in all a all n have bigger equal n epsilon, and that is bigger equal n, and for bigger equal n we have that, and now we can of course do the game that we had it backwards because that is actually what we intended to do. Uh, should be careful. Just gonna get that for now. Right. Okay, that is another thing, and now we bring that to here. All right. And now just observe that this here, if we have 1 divided by epsilon upper bracket, and of course that is bigger than 1 divided by epsilon. And by multiplying by the inverses, what happens? Well, this comes, this multiplied by the inverse is 1, and here comes the inverse to the other side, so we have 1 epsilon. Okay, let me do it slow. This number, this funny number has an inverse, right? And now we have that epsilon is indeed just multiplied on both sides by epsilon now, right? And that is exactly 1 divided by epsilon just by definition. And so that is smaller than HS, bigger equal. So you see actually such side notes, like I'm doing that in lectures, you wouldn't have that. People would just, professors would just throw it at you and say, well, it's clear, right? So, and I hope that is already clear for you, more or less. But yeah, I'm doing that stuff still. But well, I guess I will also cease doing that, and I don't know how soon, maybe soon. So yeah, be prepared for that and know that it is completely normal. Okay, and that shows the claim. Because for n bigger or equal than epsilon, we have that epsilon is bigger than n, which makes this sequence a null sequence. Right. All right. Yeah. That shows the claim. And that finishes this proof. Right. Okay. Well, now we have that convergence of the sequence. And actually, yeah, with all those explanations, we needed for that like I don't know exactly how long, but we needed long for it. For this one thing. Which is actually funny. But okay, we also like thought about some stuff that is new, like those definitions, this useful identity that we can write for it like actually this. It is used all over the place. Also factorials we have considered, some trivial steps but involving new definitions, also some comparisons. Yeah, you can take a lot from it. But yeah, be aware that this is just a proof about which you could say that's completely technical. It didn't actually require thinking. Of course, it required thinking, like thinking about how to apply the definitions properly so that the formal technical context for the results of applications of those definitions is established in such way that the needed results arise, right? Just putting application of those definitions into the proper context, and the thinking that we have done was basically restricted to thinking about those brackets. They are, by the way, are called Gauss brackets. Thinking was restricted to Gauss brackets and thinking, well, we have to choose that so that this cancels somewhere in the sum. But yeah, it's just technical stuff. We basically used addition and uh, trivial comparisons, bigger, equal. Yeah. But of course, I'm not claiming that it should be simple when one looks at that first time. It should be, of course, unfamiliar. That's completely normal. It would be actually amazing if it is, if you just see that, just like, yeah, that step works like that, that step works like that, perfectly fine. I understand that all. That's perfectly clear from the beginning. It would be amazing if it is like that. But if it is not like that, then it's completely normal. And this is the normal case. That was like that by me. But yeah, from my position, this is our technical stuff. But of course, go through steps. And if you need a couple of hours for that, that's completely normal. By that proof, I probably would have needed that myself. I probably had needed that myself in my time. So yeah, that's normal. Yeah, but overall, just keep in mind or keep in the back of your mind that it was just carrying out technical steps in the proper way. Like what we did with the limits of sequences back then with the limits arithmetics, that was much less trivial in that regard. Because yeah, we actually used addition and comparisons. Other stuff was just self-explanatory. And addition, like meaning when we add to a positive number something and just compare it with something that where nothing was added, then this addition is larger than that number where nothing was added. Yeah, comparisons like that. Yeah, but of course, yeah, as I said, many technical steps, a few of new definitions, everything applied rather fast, and many steps that I just skipped over or like only sketched them because, as you can see already, are the objects that are involved are many, but the structural connections between them that we use are rather trivial. Yeah. But there are too many to really specify them properly. All right. Like here, if I would have written down all of that, it would be just such a drag. Such a drag meaning it would have taken up too much time. Right. Just imagine a new line for each of those. Yeah. And believe me, in a lecture you would just be presented that without any such explanations, or in the best case, those explanations would have been done orally, purely orally. Well, actually, there are some professors who do it a little in that way, but yeah, it's rather rare. And I don't mean exactly in that way, like very simple steps, of course not explained because there's really no time. And you see, my lectures are really lengthy because I'm trying to explain actually a lot of stuff. And also I'm explaining stuff that hopefully doesn't need explanation anymore. Like that, for example. Yeah. Okay, well, that was the first thing on our agenda. And probably what will have to do other than that, we will continue with that next time. That is Cauchy sequences and completeness. But maybe I can give you a definition of a Cauchy sequence. So that you can contemplate it, and by that we will probably finish. I don't know. Let's see. Okay. Definition: a sequence. Of course, again, sequence and real numbers. We don't know our sequences yet, and we won't know them, I think, for a long time. A sequence an and element n is called a Cauchy sequence. are just Cauchy, so it is also used as an adjective. F, well, kind of similar like by limits, but it is now applied to the members of the sequences of the sequence and to distance between them. The distance should get small and stay small if the following is true, and correspondingly definition is like that. For all epsilon bigger than 0, there exists a number in epsilon element n such that for all m bigger or equal than epsilon, so from there onward, we just have that the definition that the distance of any two members that we take here is smaller than this epsilon. And it might be, you might think that it is quite a remarkable thing that it is not for consecutive members, but it is really for any choice of indices after that. And this is important. If you would have that for consecutive members, well, I'm not sure. Maybe it is equivalent to that, but I think no. For every epsilon, it gets the difference gets as more as possible, but only for consecutive members. Now imagine that. Well, so in the end, would it be equivalent into this definition? Let's see. I think no. But I'm not sure if I have a counterexample. Like a non-Cauchy sequence where only subsequent members, meaning they exist in epsilon such that for n and n are bigger or equal than epsilon, a n minus a n plus 1 in epsilon. Yeah. I'm not sure why it does not suffice, because that would make definition a lot simpler, because we would not have to show it for everything like that. We would have only to show that for something like that, right? And certainly you might think about triangle inequality, but triangle inequality won't work because, well, we would have to do it for infinitely many, right? Well, what would that mean? Well, that would mean that for consecutive members, I actually think that it would work, because you see, when it gets small for everything, eventually it gets very small, and like the members are closer and closer together the further we go, and then it seems to me that it must converge. But the problem is that to conclude the Cauchy property from that here, the subsequent Cauchy property, if you would, at least if we go the straightforward way, we would try to use triangle inequality, and it was, of course, not. It would not work Well, maybe it would work. If we need that, then yeah, okay. It would work because we just fix it, right? We just fix what epsilon we want. And then if we have epsilon that we want, or we'd like to show that, right? Okay, it would work. We would have just that the difference between that is just m minus n, right? And then we would have to look at our triangle inequality in terms of we would have to define that like that, to divide that like that, right? And then we would have just to go over all the steps, right, from an minus n minus 1 and plus and you would have here something like a m minus am minus 1, and here we would have multiply that by that, and that would work. So for every definite epsilon we would just have a finite number of triangle equals because we would have that. But yeah, that would be for chosen indices, right? That was exactly what I told. What I that is exactly what I'm talking about. Because for chosen epsilon, we have to find such an epsilon. So for any such distance, that we have that, and this doesn't seem to exactly work, right? Okay, I'm not sure yet why Cauchy property cannot be defined like that, because I mean, I cannot think of a case where this not give would not give a Cauchy sequence. But it seems that an elementary proof to prove that it really gives a Cauchy sequence just fails, right? So you see the problem? All right. So probably it would not, but I can hardly imagine a sequence that actually gives this subsequent condition always, but fails to satisfy the Cauchy condition. It would be rather weird, right? Because when the members get closer and closer together, okay, let's imagine that we have a sequence and it goes like that. Hmm. Yeah, okay, I see. Yeah, okay. Okay. No. Yes. No. Yes. No. No. It is just that it has to converge somehow, right? It seems that it has to converge because it would be funny if it wouldn't. But I don't see a proof for that. I don't even see an idea of a proof for it. Oh, of course, I could think of proof by contradiction, like that this would not be Cauchy, right? I mean, for something, we would have something that always remains above some epsilon. I mean, there will be always a point where it remains above some epsilon. For some, there would always be a point where it remains above epsilon. And there would always be a choice of the sequence members, no matter how far we go from where on we choose, there always will be a choice that we are bigger or equal epsilon, right? But then this condition could seemingly be true nonetheless, right? Because we could just increase it and we could take ever increasing distance, right? So I kind of fail to see how we could have a sequence that actually satisfies the subsequent condition but doesn't satisfy the condition itself. It is kind of like what it boils down to is that let's say we have a following sequence. We have something like 1/2, 1/2. I mean 1/2, 1/2 plus 1/2, 1/2 plus 1/2 plus 1/2. Then let's compare it because I'm not sure yet. Let's compare it in a different way. Compare it like that. 1 plus 1 minus 1 and right and yeah, well, and yeah, what I want to compare, well, that would be okay, of course I want, oh, it doesn't matter how, but okay, I want to make it look nicer. I want to have it like that, and that would be just 1 and plus 1, right? Yeah, that would be just this stuff, right? And then 1 and plus 1 minus 1 and plus 2 would be just sorry, do you mean that? Too fast by writing. And plus 1 would be, of course, well, another thing where we just increase it by 1 would be that, right? So that is certainly smaller than that, and that is the sequence is falling. Okay, the sequence is constantly falling, and it is pretty certain that it will reach any small value because that goes to 0 and that goes to 0. Okay, let's think, but wow. Yeah, okay. Let's think what would happen. Okay, I failed to see whether this condition would go wrong. I mean, it's very self-suggested that this condition is equivalent to Cauchy condition, right? Because it's just visually impossible to imagine that this sequence is not a Cauchy sequence. It's visually impossible to imagine. Actually, visually it is possible to imagine. Kinda. But yeah, if you think about all of them and we get closer and closer together, and kind of also know, I would like to have, yeah, what I wanted to have is that this is indeed falling, and then we can have the subsequent condition satisfied. Yeah, well, if we just add that to something, but yeah, the problem is if we just add that, okay, we have to somehow make it fluctuate away from everything. Yeah, wait, yeah, no, no. Well, let's think about this fluctuating sequence, and let's take some number, and we just will Okay, let me think about it. We are trying to find a sequence that grows larger than any epsilon when it is done like this, okay? And for that we just have to take a sequence that for each epsilon, if it is just a subsequent condition, then for each, okay, I know how we can construct such a sequence, but I'm quite unsure if it is actually properly constructible. If it is even a thing, really. You see, we just take some 1 divided by n for natural numbers, right? And we know that this gets arbitrarily small because n gets arbitrarily big, right? And we do the following. Well, we consider our sequence, and for this n, we want to have that n members of that sequence. Okay. We want to have that n members of that sequence have distance 1. And how do we do that? Well, no, sorry, n members of that sequence. I mean n consecutive members like n a, let's say k, k plus 1, k plus well, I actually need, or I want to have that we have exactly, if I take k plus n, that, well, does not suffice. For example, for k plus 1, I have k plus 1 minus k. Okay, that would be 1. And here, yeah, indeed, we have k plus n. Okay, and we want to have the following. We want to have that this distance is actually equal 1 divided by n. And this distance is actually equal 1 divided by n. So you see, for those n, we have then that this, okay, wow, that is only an upper estimate, right? It would be not, that would be only an upper estimate, but we need a lower estimate. Okay, well, that is more difficult than I thought. But okay, well, go differently. Okay, and that works. So that is truly, we would like to have, or it doesn't matter actually how I have that, because we could choose that, right? AK minus AK plus n. Right, and that would be now AK plus n minus AK plus AK plus n minus 1 minus AK plus n. Right, and that is now exactly that, right? That's just eliminates, that eliminates, and so on, leaving only that. Right, and now if that distance was constantly equal to 1 divided by n, exactly those n members, and those have distance 1. And now imagine for each natural number, how could we do that? Well, how could we do that? We could just say, and then we have 1 and plus 1 for those subsequent, and so on, right? So that for all subsequent, but here we have to be careful. If ak plus n minus 1 minus ak plus n equal to 1n plus ak plus n minus ak plus n plus 1, that is equal to 1 divided by n plus 1. And unfortunately, this distance would be larger than 1 divided by n. So we have to somehow, maybe we can alternate them. And it will be certainly smaller. And when we have then another one, that would be equal, right? It will be again smaller, right? And we could alternate them, seemingly. And that would give us nonetheless what we want, because any consecutive ones would have that property minus 1 and plus 1 plus 1 and plus 2 would be, that is of course smaller than that, and then the absolute value of that is more than that. Yes, okay, now how do we define such sequence? Well, a way to define such sequence, let me think about it a little. For it is not that easy for, okay, let's try to do it just a simple way. If we start by 1/2, for example, then we have that this difference has to be 1/2, and this difference has to be 1/2, right? We have gone from a 0 to a 1. Right, that is from 0 to a 1. 0, a 1. So we have to go to a 2. But well, that is already, something is not right. Have AK. Actually, we should go from there to there, because we would raise too many. Oh no, we would not have too many, or would we have too many? Oh, if we go for 1, we would have only 1. If we go for 2, then we would have 2. Right, so for n equal 2, we would have to go for 0, 1, and 2. Right, and that would be 1/2, meaning that a 0 minus a1 minus a2 is 1/2. Okay, if we, for example, take 0 here, of course we have to take not 0, but for example 1/2 here, Oh, 0 minus 1/2, whatever, but I don't like to go into a negative, so let's try to stay positive, and I think we'll succeed at staying positive. Ah, no, with the sequence itself, no. So what is happening? We are at 0, and now here we are 1/2. So that would 1, 0, 1/2, 0, 1/2. Okay, but then, but that sequence should converge. That sequence should be a Cauchy sequence. Hmm. 4 minus 5. Yes. That would be minus 1/3. Minus 1/3. Minus 1/3. Ah, maybe I have estimated its dynamics prematurely. That would be minus 1/3. And so what we have to take here would be minus something, so that 1/3 rises. Minus something, so that we have 1/2 plus 1/3 is 5/6 for something. I think 5/6, yes, because we have to take 1/2 away. So, oh, you see, something interesting is happening. Here we have, and of course that is 5/6 positive, right? Okay, that is 5/6. We know that. That was 1/2, and that is 5/6. Right. I do not quite like this, because we could consider now. Ah, right, because it goes smoothly from there to there. So there's no need to consider that. Ah, yeah, there is a need to consider that. No, there is none. Let's think a little bit. Um, we have 5/6. 5/6, and here we have 1/3. Here we have something like minus 1/3 we want to get. We have 5/6, want to do away with 5/6, and that is 6, 6 here, 18 here, like 18/6 or something, because we need 15/6 and we need 1/3. Yeah, so yeah, just to think that we have that, and you see the sequence actually would grow out of proportion in order to allow that. That is interesting. Interesting is also that I thought that we have to do that in order to have to give that difference. But no, we don't have to give the difference, because we don't need a Cauchy sequence. We need a sequence that only the consecutive ones are given in a certain way. And let's try to derive what we actually want to have. Well, if a 0 is 1/2 and a 1 is 1/2 and a 2 is minus 1/2 and a 3 is 5/6 and a 4 is 18/6, then it looks kind of like of course the first one is chosen arbitrarily, right? But then we just keep, if we wanted to have from the difference, right? we have a difference, and we'd like to obtain the thing that we like to have it here, then we would have to obtain from this difference exactly the minus, oh no, we would have to obtain the plus. Okay, I got confused. We want to have that, right? If we want to have that, then we have to take minus the difference, and have to add a 0, right? Minus the difference, would be that, right? The difference is 1/2, and minus the difference would be 0 plus 1/2, but well, that would give us a 0, and we want to get 0 out of the difference, right? And then we take the difference of those members, and we want to take the we want to get the member a1, but then yes, we would have to take minus, right? Get minus 1/2, and then add the difference, right? So everything is fine. Minus a 0, minus 1, right? And we would add a 0. Right, and now we would go further, obtaining minus but don't forget, that was the prescription for if we have differences, we have prescribed the differences, we can define the sequence as like this is a given thing, right? This is difference 1 is equal to d1. Well, since the difference here is supposed to be 1/2, let's just call it d2. Just define it as d2, right? So the d2 is given, and then we'd like to, well, then if d2 is given, then minus d2 plus a0. Now we have this d3 or something. And now how do we obtain a3 from a2? Well, we just take again, so the idea is always the same, but the differences, the sequence of differences is given as d1, d2, 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 d3, 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 d4, 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 and that corresponds to a 0 minus a1 as we defined it, right? And that corresponds to a1 minus a2, and that corresponds to a2 minus a3, that corresponds to a3 minus a4, and that corresponds to a4 minus a5, and so it goes on. And now we'd like to define such a sequence. Right, it is not difficult to just see that when such a sequence of differences is given, then if the starting thing is that, right? So, yeah, but the problematic part is we don't know from where we go again. Huh. Yeah, that's the problem, that we have to keep that for exactly as many members as ta ta ta, right? How do we define something like that? Clearly, it is how we define it, it is well defined, but how to put it into mathematical language? That's a good question. Well, we could notice something, right? 2 we have for 0, 1, 2. Right, and 0, 1, 2, 0, 1, 2, 3, we have 2, 2, 3, 4, 5. Okay, I mean, D2 from D2, 3 from D3, and so on. Alright, so it kind of those are the okay, I would like to reference a certain topic, but I can't because we don't know about this topic anything yet. But okay, well, 2. Here it starts by 0 and it goes 0, 1, 2. Okay, then we go 2, we go to 3. Right, and then we just keep turning around our differences and adding the member that is already known, but only for a certain amount of times, right? And for a certain amount of times, namely for the current amount of times. So for 1/2, we do it 3 times, and then the new members of the sequence begin. The members given by the new rule. But as you can see, the problem that rises when we try to define such a sequence explicitly is that we should keep track of where we are in the current proceeding um, of using the previous fraction, right? Okay, so how do you define such a sequence actually? Well, the trick is we cannot even truly define it recursively because even by recursion we would have to keep a track, to keep the track of these numbers, right? So let's define our sequence Dn first. How do we actually define that sequence? That is also a good question. Well, for the D2, so just first define a sequence D tilde, and then let's say bigger or equal 2 is equal to 1 divided by n. Okay, that is our familiar sequence. But now we'd like to have it repeated a certain number of times. First, define it informally. 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4, and so on it goes on. And let's define it formally. The question is how? How could we keep track of how many times we have used that? Well, if I don't use that topic, what could I do? Okay, let me think. Okay, so we see that we should somehow use the properties of natural numbers to make it happen. In some way, we should assign those things to those, right? And we should kind of, we know that when, with which happens when we have done it a certain number of times, starting by the current by the application of current fraction, right? After a certain number of applications, that there starts a new one, right? Okay, how could we do that? Well, um, seemingly we should characterize somehow explicitly those certain sets, consecutive sets of numbers, right? And what could we do for that? Well, we could observe the following. Um, no, I would like to do it like that, but it wouldn't work. I think we should do just a simple thing and look at how we shift it. Right, so here it is kind of shifted by 2. And don't pay attention to what I'm saying now. It is shifted by 2. Here it is shifted by 1. So it's kind of like the last thing. So here it is shifted by 1. By 1 to the direction of 1 above. Here it is shifted by being double multiple. Here it is shifted by 9, 10, 11, 12, 13, and we are now at a number 5. So at 5, it will be shifted by 4. No, at 5, it will be shifted by 3 now. So here we have a shift, 1 downward. So you see, it is kind of the numbers that we go through here. 1 downward from the number in the denominator multiplied by 1, right? Here we have, okay, we have to keep track of both. Okay, oh, okay. We see it is difficult to describe the sequence explicitly. We could do that, but it requires some work. It requires some new work, technical albeit, but nonetheless, it requires work. So to describe such a sequence is a little bit tiring. But let's see if we go get away with an index shift easy. 3, 4, 5, 6, 7, 8. I think we just might get away with an index shift easy. 1, 1, 2. Let's shift the index. We start our sequence at 1 in natural numbers. So it's 1 short of the double of the denominator, right? 6, 7, 8, 9. Okay, that's 1 above the double of the denominator. 10, 11, 12, 13, 14. That's one short of the triple. Okay, let's start our sequence by no, it would not work. I think no matter what I do in that regard, it would not work. So here we would have double. Here we would be 2 above. Here we would have triple. Here we would be 2 above. Let's shift another time. Here would be 2. Here would be 3. But here would be now 4, 5, 6, right? So we are double. 4, 5, 6 would be double, right? And here's 7, 8, 9, 10. We would be 2 above. 2 above multiple of this by 2, right? And here we would be triple. So now not double, but triple. And here we should be 3 above, right? Let's continue it like that, but we keep in mind that we shift it. Wonderful. We are 3 above. Yes, we are 3 above. So that works. That works just fine. Let's try to drill it down. What we want to have, we want to start our sequence by 2. And let me write it down again. What we then have. So let us start with sequence by 2. And to just specify those 1/2 explicitly, and then continue. Okay, that's rather lengthy, but okay, we'll be rewarded for that. Okay, we start with sequence by 2, and now our correspondence is that. And pay attention to this. And actually, we could also start, we could also not specify when explicitly, because that is just 2 plus 1, right? Here. And here, our designated thing is 2, right? Because we have 2 here. Here, our designated thing is 3, and we have multiple of 3 by 2. Here, we have 7, 8, 9, 10, and we have 2 multiplied by 4, and we are 2 above. Right. Here, we have our 11, 12, 13, 14, 15, and we are by multiply of 5 by 3. And we have a strong suspicion that the sequence will go onward like that. Here we are by multiple 3, and we are 3 above. And we have a strong suspicion that the sequence will go on and will define it like that. Right. So the idea is just to first define this sequence, right? First we define this sequence, and how do we define that? Oh, this is kind of already specified. The question is just for what number we define it how, right? And we see always there is some kind of true, and some things are increasing, right? Some things are increasing, and how are they increasing? Well, we have some alteration. Like here we just added 1 to this. Here we took a multiple of the next natural number by 2. Here we took, so here kind of multiple by 1, right? Okay, here multiple by 1. Here multiple by 1 and plus 1. Here multiple by 2 and plus 2. Here multiple by 3, just like here multiple by 1. Oh, that is confusing. Okay, so observe that. Here multiple by 3 or 5, and here we have multiple of 6 by 3, and now plus 3. So we have a strong hypothesis that this sequence of wished differences actually has somewhat like, we have not specified yet for how long, but it has some kind of where k is increasing. We have not specified yet for what indices, but it is somewhat like this. Right? Yeah, and we should specify the numbers to which it relates like that. Right? It's the number to which it relates, and this goes, and this is how this goes on for some natural numbers, right, in our sequence. Okay, and now here we specify the number to which it relates, and let's call that in L. So there are two things going on. They are of course connected by how the indices interchange, and yeah, that is how it goes. And yeah, we should also say that this is just our natural numbers, right? So this is just natural numbers. Well, and this is the final thing at which we finish, right? So the thing at which we finish is given by such n. Let's call it m. So, and now we have those alterations. We go through n's, certain kinds. That was exactly through 2 n's we have gone. Here we have gone through 3 n's. Here we have gone through 4 n's. So it kind of alternates, right? Here we have gone through 5. And let's try to describe it. Well, what it looks like is it kind of still dependent on it because we have that. But let's see where we finish. Because that is also a matter of interest. We have to see how far we go and where we start compared to where we finish. Right, and that is... we have yet to think about how to think about it. Right, in comparison to other stuff. 3, 5. 3, 5. Here we had just 2. Well, actually, no. Yes, but yeah, we have to think about it because we could describe it with the lower stuff. We could describe it with the upper stuff. So we have to be careful here. We have to be careful here. have to describe that by that. 2 multiplied by 1 plus 1 is exactly this 3, right? And we kind of start by 2, and we know that we have to go by 2, but we have to describe it in proper terms, right? So now we have that 2 by 3. And then it is clear how to continue this sequence. We could continue this sequence, right? But how do we define it? Well, not so easy. Not as easy as I thought. We have to really think how to do that, what properties of numbers to use. But, well, for all numbers, that here, well, that is actually simple. We just don't know how to start that. But this from here to here, that should be simple because that would be just the number, what that is the number previous to no, the number subsequent to the previous multiple, right? So those parts is easy because we just have to take a previous multiple plus 1. Maybe here a previous multiple plus 2 actually. Pre 5. No, previous multiple plus 1. It would be exactly previous multiple plus 1. Okay, so kind of kn plus 1 is the number, and then k plus 1 n. That would be the that would be going through such things when we know where they start, right? So k kind of goes, k depends on the current number, and n also depends. Yeah, n and k are both dynamical. You see, n and k are both dynamical because here we finish and here we start our next one, right? And next one is exactly that previous multiple, but yeah, there are just too many coefficients, but we have to keep track of all of them, and we have to find their dependencies, right? So we have, let's put it like that, and maybe some of them are connected. We will see. So first of all, we have this 2 divided by 1 plus 1. Now after some time, we have that was 2 multiplied by 1 plus 1, right? Okay. After some time, we have 2 multiplied by 4 plus 2. Wait, but this doesn't... yes. The thing is 2 stays the same, and this increases. So this 2 stays the same. Let's denote it by p, permanent. Those are permanent. It will be always 2, right? And those are increasing, right? And they are increasing with certain interval that we have somehow to express. Right, and that would be 3, 5, and that would be 3, 6 plus 3. Oh, no, because that is 3, 6 plus 3. Ah, yeah, sorry, Chris, that is not right. That is not permanent. Nothing here is permanent. Everything here is increasing with a certain I have to pay attention that that is 2 multiplied by 1, right? So 2 is our number. 2 is the number here, right? Here we have 2 multiplied by 3. Here we have 4 multiplied by 2. Right? So the row of 1 is here played by 2. So 4. And here we already have that that is actually either multiplied by 2 plus 2. Don't know yet. We have that. All right. So, and that strongly suggests that this is actually plus 2. Here we have 6 multiplied by 3 plus 3. So we kind of have plus 2. This is our hypothesis, and our hypothesis is that it wouldn't change. But of course, we would have to prove it by induction if we wanted to do it rigorously. Okay, this is one tendency, and this happens every ta-ta-ta, we don't know what. Maybe this distance, this interval is also increasing or somehow depending on something. We don't know that, but yeah, that is one tendency. And another tendency is just multiples of odd numbers, right? So next we expect like 4, 7, right? Here we had 2, 3, and here we would 3, 5, and here we would expect 4, 7, right? So what we have here again, just write those numbers here. The relevant numbers are written here, and the changing numbers are written here, right? Of course, those are also changing, but they are changing like by certain procedure. Right, and of course we expect a 7. Okay, no, and that is now multiplied by 3, and that is changing, and that is kind of fixed. Okay, now the interval. Maybe do let 7 to be convinced that we really have that. But I'm pretty certain yes, but yeah, let's do that. 7, 7, 1, 7, 7. Oh, we could have, of course, a sort of 7, but yeah, so it is more striking. 22, 23, 24, 25, 26, 27, 28, 4, 7. Indeed, next up is 7 after 5. Okay, so and now we'd like to know what is actually happening. All right, here we had that. We have how many tendencies? Well, here we have one tendency. 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 But those tendencies are kind of parallel, right? We just take the numbers 2, 4, 6. Here we take the intermediate ones 3, 5, 7. That kind of works. That we can do. Those sequences we know. There's even and odd numbers. No problem with that. All right. But now, through how many do we go? Well, here we go through 2. Here we go through 3. So if we write those down, then here we went through 2 numbers. Here we went for 4 numbers. Here we went through 6 numbers. All right. But now how to determine those exact intervals? That's the question. Also, here we don't know the interval. Right. Well, we just had that we go here by this, and by this was concerning the last number in the row, right? But if we just look at through what we go, then we go from 2 ta 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 to 2 plus 1 plus 1. Right? So then the next one should be, of course, the other one, so that should be multiple 3. And here we go from the one at which we finished. So that is 3 plus 1. And here we go to 2 multiple 3. 2 multiplied by 3. So if we wanted to know for a natural number where it is, we would like to have, for a natural number, we would like to know where it is. And we would like to know, of course, where the previous one has finished and how much we have proceeded since then. So first, let's try maybe recursively. And recursively, we would do what? Well, recursively, we would look at, well, where have we finished? But the thing is, there are just too many processes going on simultaneously, right? We would like to connect them. And here is already a nice connection, right? And so this process is kind of clear. This process is also kind of clear. And we already know that there is 7. So the only things that are not clear, completely unclear, are the intervals. Let's try to deduce the intervals from what is happening here. Right. What do we mean by trying to deduce the intervals? Well, we actually mean that we have to understand what number we are dealing with as an explicit thing, not recursive. But first, do recursive. Do it recursive. Okay, recursively, what does it mean? Well, we know a certain number of previous members, and from them we can compute our current member of the sequence. Right. For example, if we have n4, right, then it should be 1/3, but more precisely, it should be d3. For a4, we should have d3, and for knowing that we have d3, we should know that before that, okay, I see how we can define it recursively, but yeah, it is really problematic. We can now write first a recursive rule that is really extensive, like it would be something like very large. Yeah. Why did we actually start to try to analyze the sequence? I wanted to give you an example of a sequence that satisfies the subsequent member condition but is nonetheless not a Cauchy sequence. We could do that. Maybe I'll do that in detail in one video, but yeah, it's becoming really lengthy, and I think at that point I would like to do it really myself and only answer that, present that, because that is a lot. I won't be able to to figure it out in this video, unfortunately. I have to think about it myself if we even want to do that. But yeah, pretty sure after we have defined that sequence and we kind of see that we can define it, right? This is a proper sequence that is defined somehow in the recursive way, albeit, but yeah, it is a proper sequence that is defined. And I think there is also a theorem that any recursively definable sequence can be defined also in an explicit way, but yeah. Uh, yeah, okay. Well, so this defines a sequence, and then with those fractions, we can define also this sequence recursively by this sequence, and that would give sequence that is not Cauchy sequence but satisfies the subsequent member condition. What that would be? Well, that would be something funny, as you can see here, but it's just, yeah, it would work. It would go up and down somehow, and yeah, you see that here it increases very strongly. And 18.6. And now you have already to, that is very, very free. Now you have already free 1/3 or something. But now to keep that down, you have to take your A6 being something like 1/4, and that with plus, and that is actually A5 minus A6. And so that we have to take that again larger, actually. No, smaller than that, yeah. Smaller than that. And what you would have, well, you would have 10/3. And you would have to leave 1/4, so you have 10/3 plus 1/4 is, well, 43, 43/12. I don't want to calculate that. 43/12. No, you have to take minus 1/4, actually. You have to take minus 1/4, of course. So you have 37/12. Sorry, you have, yeah, you must have 37/12, and because you have 10 4th, yeah, 37/12, and that is of course just 13/112, and you have here again some things a little bit smaller than that, and then it goes on, and you have something again a little bit smaller, and so on. And so you can see this sequence is actually not a Cauchy sequence, because it will go completely out of control. This degrees will not suffice. I guess this sequence will actually, in the end, this sequence will even go to infinity, because this increase kind of suggests that. I think this sequence will go to infinity, because you see those consecutive increases, we will just add up to 1. It will add up to 1, so that the difference of your subsequent sequence members, we have chosen them to add up to 1, right? So the difference of your subsequent sequence members, yeah, to -1 and to 1. So it is, yeah, it is weird. It's certainly not a Cauchy sequence. and you see that your difference is kind of like that, but we don't see yet if it is divergent. But here we will see if a sequence is not a Cauchy sequence, then it is divergent. We will even see that that convergence is equivalent in R to being a Cauchy sequence. Okay, yeah, this I didn't finish, and I don't know if I intend to. It got way too much to do, because to keep track of all those dynamics, yeah, it's kind of hard. I can't do that without proper analysis of a situation. Yeah, but yeah, we can see that the sequence can be defined, and it is not a Cauchy sequence, but it satisfies the subsequent condition. So the subsequent condition is indeed not sufficient. Okay. Okay, so we have need to require for all in M equal epsilon. Okay, now with that I just finish, and next time we will continue with Cauchy sequences, accumulation points, and equivalence of being Cauchy sequence and convergence of a sequence.